Hello, BC Calc. I hope your quiz went well today. I know my other class was complaining about it. I hope it wasn't too rough. I wanted to give you a little screencast of what the other period, my upstairs period, did the other day. And hopefully this will make sense. So those of you that took AB Calculus last year probably remember some of Rolle's theorem, but we'll review it just a little bit. Both of the things we're going to talk about today are very, very intuitive, and it's unlikely that you'd see anything, a free response question or anything on the AP that have to do with them, but you might well see a multiple choice that sort of asks you to use them indirectly. Okay, so Rolle's theorem. Let f of x be continuous on the interval AB, right? That's inclusive there, and differentiable on the non-inclusive interval AB. And we'll talk about what that means in a second with f of A equal to f of B equals 0. So that means we have two zeros, one at A, one at B. There could be others. We just know that we have those two. So a continuous function, right? Continuous, right? That means the limit as f approaches from the left at a point has to equal the limit as we approach from the right, and has to equal the actual value at that point, remember? And we can sort of think of continuous as a function I can draw without picking up my pen at all between 2 points A and B, right? I could have jagged edges, I could have any of those things, but I cannot pick up my pen in between, so no jumps, no holes, none of that. And differentiable, right? Remember we saw when we were talking about functions that are differentiable, we saw things that weren't differentiable, and those were things with jagged edges, right? Jagged edges like the absolute value of x, right? At 0, that is not differentiable because there's no single line that's tangent to the point. So differentiable, we really think this thing is smooth, right? Smooth, no jagged corners or anything. So we have a function here that is continuous, meaning we can draw without lifting up our pen, and differentiable, meaning it's smooth, with f of A and f of B both being equal to 0. So let's draw an example of that. Let's try to draw the function. Well, let's just draw a general one, right? A general one. So I know I have some function, and I have a 0 over here, and a 0 maybe here. And I have no idea what it does in between. It could go up, it could go down, right? But let's sort of draw it like this. Here's my function, here's my A, here's my B. Again, it could go up, it could go down. We don't really care. And then the meat of the theorem says there exists at least one point C on that interval AB such that f prime of C equals 0, right? And so remember, f prime of C equals 0, we're saying the tangent line is horizontal. And when you think about it, this should be obvious, right? Obviously, here would be my point C, right? Because up here, the tangent line is horizontal. And this should be very, very obvious to you, right? Because if we think about it, if f is 0 at both A and B, right? It could go up in the middle, it could go down in the middle. Let's say it goes up. If f goes up in the middle, right? If it goes up from A, well, then there has to be a point where it has to turn around to go down to B. Right, it has to turn around to go down to B, because we know f of B is also 0. And at that turnaround point, because our function is continuous and differentiable, we know that there has to be some point, a turnaround point that's smooth, where my tangent line is 0. Similarly, if f went down first, right, if f came down first, like this green curve here, right, and it came up to B, right, if we came down, we know we'd have to come back up at some point. Now, obviously, if I went down and up, sort of like a sine curve, we'd have multiple points C where f prime of C was equal to 0. And lastly, right, we said if it goes up, we have to come down, right? What goes up must come down. What goes down must come back up. If we stayed at 0 the whole time, obviously, every point on the interval would have a derivative of 0. So let's think about an example. And to prove these examples, right, we sort of just have to find the point where the derivative is 0. So let's think about f of x being x squared minus, we'll do 5x minus 24. Okay, so first we have to say, oh, does this thing even have two zeros? And of course it does, right? If we factor into x minus 8 and x plus 3, it's 0 at negative 3 and 8. So we can let a be negative 3 and b be equal to 8, and we can graph this. This thing is, of course, an upward-facing parabola with zeros at negative 3 and 8. Okay, because it's going to be symmetrical, right, because it's a parabola, we can just know, right, that the vertex is going to be at maybe 2.5, right? We know it's going to be at 2.5 because that's sort of right in between negative 8 and 3. Negative 3 and 8. Right, so it's going to look something like this. Pretend that, goes through that point. Here's A, and here's B. Okay, and it's plain to see, obviously, right, where this derivative is going to be equal to 0, right? It's going to be equal to 0 at this point, at the vertex. I'm going to have a tangent line that's horizontal, right? Again, this theorem seems kind of dumb. We can think about this, as a JV theorem if we really want to think about it. It's kind of mean to the theorem itself, but it's okay. We'll do a varsity one in a second. So how would we show this? Well, we'd have to show that there exists some f prime of x that equals 0, right? That's what this says, right? That's what the theorem says, that f prime of c equals 0 for some c in between a and b. So we know f prime is just 2x minus 5, and we're saying, oh, look, that's 0 here, so we're going to get that point at 2.5, as we said earlier, at the vertex at 5 halves. And so c, right, c would be the 5 halves, 5 halves being the point that would satisfy Rolle's theorem. Okay, so this is a very, very specific case of the varsity theorem that we're about to talk about, called the mean value theorem, or MVT. Okay, it's quite a bit more powerful, right? And this theorem, Rolle's theorem, really relied on a very specific case where a and b, f of a and f of b were both 0, right? So there was sort of no overall change as the function moved from a to b as a whole, right? It might do something in between, but the values of the function at a and b were the same. They were both 0. So let's look at the mean value theorem down here. Okay, so we have the same conditions. F of x is continuous on the interval and differentiable on the non-inclusive interval. Then there exists at least one point c on a comma b, such that the derivative at c, f prime of c, is equal to f of b minus f of a over b minus a. Let's talk about what this right side of the equation even means. Okay, what does this right side of the equation even mean? So if I have some function, I don't know what it looks like. Maybe it comes down. Here's my function, right? Who knows? And I pick some a here and some b over here, right? This point here is a comma f of a. If this is a and this is b. And this here is b comma f of b. So if we remember back to our Algebra 1 days, when we had this notion of slope, right? If I asked you to calculate the slope, we call this a secant line. Secant line. That just means intersects in at least two places. This secant line, right? If I asked you to calculate the slope of that, you would say, oh, it's the change in y's over the change in x, right? It's the change in y over the change in x. So m would be the change in y over the change in x, which of course is f of b minus f of a over b minus a. Look at that, right? This is the exact expression we had up here, right? And that is the slope of the secant line between these 2 points. Or we can really think about this, convince yourself of this, that this is the average rate of change. The average rate of change. Okay, it's the average rate of change over this interval, AB, right? It's the average rate of change because it's saying, hey, how far did I go in the y direction? And then divided by how far I went in the x direction. That should not be all that earth-shattering to you. And this theorem simply says that, hey, on some interval AB, there's going to be some point in the middle where my derivative at that point, my tangent line at that point, has to equal the average rate of change. So maybe that would be right here if we were to draw that on this point. Right here, the average rate of, or the rate of change at that exact point might equal, the slope might equal the average rate of change on that whole interval. Okay, and why does this make sense? Very similar to our Rolle's theorem up above, right? The JV theorem over there, right? Rolle's theorem said, oh, if I have no change from A to B, right? If they're both 0, then at some point I have to have a rate of change of 0, right? So this thing says, okay, I can pick anything, right? Maybe my average rate of change is 7. Well, then there has to be some point where my actual rate of change is 7 in between there. And we can use a similar argument to the what comes up must come down argument that we used for Rolle's theorem to sort of justify this in our minds, right? Either off of this curve, right, if we zoom way in, right, if we zoom way in and I say, here are my 2 points, here's my secant line, right, we can see that this is sort of my average rate of change is the slope of this line. Either I start off gaining not quickly enough, right, like this line here, right, in which case for me to get up to B, and for me to get up to f of b up here, I'm going to need to speed up how fast I change, right? I'm going to need to speed up because I'm behind right now. I need to speed up. In which case, there's some point here where, oh, we had to equal exactly this average because we started off too slow, growing too slowly, and then we had to grow too fast to pick it up. Obviously, there was some point in the middle where our growth sort of was the exact average. Similarly, if I start off growing too fast, we'll do this one in green. If I start off growing too fast, at some point I gotta say, uh-oh, I'm growing way too fast. I gotta slow down. So we get this little football picture here, right? And, at some point here, if we were to draw the slope of the tangent line, it would be parallel to both my blue line and my black line here, right? So either way, if I start off growing too slow or too fast, at some point I sort of have to overcorrect, right? Or not overcorrect, I have to correct. And obviously, if we just stayed on the tangent line, if this was a linear function, we'd have that average rate of change the entire time. So again, that's sort of how we justify it in our heads. Let's do an example. I'll do the example that my other class picked. So we thought about the function f of x equals x cubed minus 4x. So let's first, do a little pre-calc review and talk about how we graph this, right? We'd factor it. We'd x squared minus 4 times x. And of course, that's x plus 2 and x minus 2. So this thing has 3 zeros. You can picture me doing my little silly dance with my arms to illustrate that this thing goes up to the right and down to the left. So this thing looks something like this, right? It goes up to the right, it goes down to the left, and in the middle it sort of does this, right? Okay, so I let my other class pick my values for A and B. You can pick whatever you want here. I believe they picked -2 for A and 3 for B. Those were the values that my other class picked, so those are the ones we're going to use. So this guy right here is A. Again, we didn't have to pick a 0, they just did. And this guy out here is B. This guy out here, sorry, not that. This guy here is B. This is f of B up here. Okay. And we can draw the secant line, and obviously it's going to intersect the curve more than twice, but that doesn't matter. Here we are, okay? And so we are saying that in between A and B, there's some point where the derivative, right, is going to have a slope that is equal to this average rate of change. So let's first find that average rate of change. So the average rate of change, or f of b minus f of a over b minus a, right? Change in y's over change in x. Of course, if I plug in b for this thing, I get 27 minus 12, that's 15. We know f of a is just 0. And on the bottom, I would get 3 minus negative 2. So I get 15 over 5, or just 3. And, I know this doesn't look like 15 here, but this is really the point, 3 comma 15. And this is really the point, negative 2 comma 0. And you should be able to convince yourself right now that, again, not to scale at all, that on that interval, a to b, right, each time x goes up 1, I'm going up an average of 3 units in the y direction, right? 3 is my average rate of change. So the question is, how many points are there in between a and b where the slope of my derivative, or not the slope of my derivative, the slope of my tangent line, or my derivative, is equal to 3, right? How many times is my derivative, or the slope of my tangent line, equal to 3 between a and b? So let's do that out. The derivative f prime of x is just 3x squared minus 4. And we're saying how many times is this thing equal to 3? Not 0, right? We're not finding an inflection point here. We're trying to find how many times it's equal to the average rate of change. Okay? I think we're going to get 2 answers here. We don't have to get 2. The mean value theorem, of course, just says there exists at least 1, right? But here we're actually going to get 2 answers, and we'll see them and graph them shortly. So this is really saying when is 3x squared equal to 7? And here we can blame my other class. I wanted to use the same numbers in case they want to watch this video too. That we're going to get x equals plus or minus root 7 over 3. Now, root 7 over 3, if, we can talk about it. It's 7 over 3 is just a little bit bigger than 2, right? So if we want to talk about what 7 divided by 3 is, that's just 2 1/3. And if we were to take the square root of that, we're going to ballpark it, right? This is about 1.5. I think it's a little bit more, but now we're trying to do it in our heads, and that's messy. So about 1.5. And let's think about what that means. That's saying that that f prime of about negative 1.5 is equal to 3, and f prime of about 1.5 equals 3. I should really use wavy things here because we're estimating here. Really, if we put in negative 7/3 or negative root 7/3, we would get the right answer. Okay, so let's look at our graph and see if we can see that. Okay, let's draw some tangent lines in red here. So negative 1.5, that's like out here. Do we buy that the tangent line very close to that could be have the same slope as this secant line? I certainly do, right? Look, it looks, certainly there's some point in there that has a slope of 3. And again, at positive 1/2, my function's very boxy over here, but at positive 1.5, that's over here, right? Do I have another line where my tangent line could have the same slope? And that's, very, very plausible that we could. All right. I think that's about it. I hope that this covered some review for my AB friends, and I don't believe TIC had seen this before. But, these 2 theorems aren't really all that crazy. I will see you tomorrow. That would be Friday for our introduction to antiderivatives for our people that have not seen them before. So I think I posted a couple problems here. Look them over. Again, hope the quiz went well. You'll get it back from me hopefully Friday if I have time to grade them right before class. Again, I'm probably not going to get them until Friday morning. All right.